This is IAT355 Visual Analytics Lecture 8.2, where we're continuing our conversation about interaction. In this lecture segment, we're going to be talking about selection and tooltips, which is very kind of narrowly focused, but there's a few things to say about it, so let's get started. So what we're doing here is focusing really on this segment, this portion of Munzner's Chapter 11, where she's focusing on the task of selection. The task of selection sounds straightforward, but what we're going to do is talk about what you do with selection and how it leads to the other interactions. Typically, selection is focused on a chunk of data or some small number of chunks of data in order to do something with them. So let's talk about that. So selection is what we mean by that is using a pointer, typically a pointer, to select or identify an element or perhaps more than one element. And it often leads to drill down for more details. And selection is actually a fundamental task. It's a task, it's one of the first, formally identified tasks in the early interactive study and formalization work that was done throughout the 1970s. And I'm just pointing it out here that it's so fundamental that we take it for granted and we tend not to think about it. But anyway, this is something that we're going to spend a little bit of time talking about right now. So the basic pointing methods are, first, you're using a pointer in the case of the mouse or stylus or something like that, that nominally you treat as a point. That's what's meant here by point selection. The mouse either mouse cursor hovers over some target, or you click on some target. There is an overlap of the point to the non-zero area of the target item, whatever it may be, and the machinery responds to you to see, yep, you got something here. Another variation, of course, is either touching or tapping. Strictly speaking, if you're if you're using your fingertip to interact, your fingertip actually has some area, although often, it's approximated down to a point, which is the center of the image of your fingertip on the touchpad area. The third kind of point selection thing is selecting a nearby element. Even with mouse pointers, or a stylus, there is a tendency for there to be some kind of noise or a jitter or that kind of thing. So it's not a perfectly point that's perfectly still. It's something that's moving around slightly. So no matter what the interaction is, then that needs to be accounted for. But all of that accounting is taking place underneath, kind of in the operating system, in the interactive mechanics of the operating system. It's not something you yourself typically have to concern yourself with. If you're doing VR, you do have to care about that, because the techniques are still being fully developed in the field of virtual environments. The second domain is region selection, and that's the classic rubber banding or lassoing activity. That is to say, you drag the cursor from one corner to another of a rectangle, or perhaps are sweeping out a circle or an ellipse or something like that, and whatever's falling within that geometry that you're sweeping out, that's what you're selecting. And sometimes you do see that, and we'll show examples later on when we're talking about brushing and linking. Area cursors used as brushes, so to speak, that link to something else. Brushing and linking is a formal term in Viz, but I'm saying brushes because they don't look like brushes, but they have a similar kind of activity where you're touching lots of stuff at once. Another thing that typically you see with selection is set selection for the purposes of aggregating, putting a bunch of stuff together. That is to say, you select a bunch of things, and then what you want to do with that is you want a compute aggregate, compute derived value type of thing to happen. That's not something that you would get by default. That's something that you would presumably set a mode in order to say, this interaction I'm about to now do, I want aggregation to occur. Part of the reason for doing this, of course, is there's some kind of detail that you're interested in and you want to keep track of it, particularly if there's a lot of distractors. Think of all the streets in our fair cities. You might have the name in mind, but you might not, and you want to keep your finger on it, or perhaps a particular location on Broadway or on King George, and you want to. I want that white spot. I just need that thing, and you don't want to lose it. In particular, you don't want to lose it in the domain of the work that you're doing. That is to say, in the underlying geographic information in the case of maps, or inside the data set that you're interacting with. So closely related, of course, to selection is tooltips, and we saw an example in the dancing histograms, of course. The purpose of tooltips is to tell you a little bit more about what is present in the underlying data. In the visualization case, it's typically to say, to put in writing, at least temporarily, the details of the piece of data that you're hovering your mouse over. Typically, it comes up automatically. So here's something in which, the type is health, the calories is 105, average fat is 1.1, etc., etc. I'm hovering above something, and it's telling me the details about this particular thing. And that's hovering above one of these, probably this orange bar right here, and I get a tooltip telling me all about that orange bar. So selection is something that you can do a little bit more with, and what I'd like to do now is show you a video. The video is a bit old. It was shot on VHS, but it kind of illustrates kind of nicely the way in which you can do interesting things even with a two-dimensional display like this thing. So this thing here is called TableLens. It was built at Xerox Palo Alto Research Center, which was, this and a few other techniques were spun out to a small company called Insight, which became a modest-sized company, which was bought by somebody that bought by SAP. And so this is now in SAP's suite of tools. So what we're going to do now is we're going to switch gears and watch that. Okay, so here's the video. This is, as I said, was made in 1994. So it's on VHS, and so a little less than 100% ideal, but professionally made for its era.
In an information-rich world, the problem is not so much acquiring information. The problem is more making sense of large amounts of it. In our user interface research group at Xerox PARC, we've been exploring the use of information visualization to produce new kinds of documents and new user interface paradigms that allow people to deal with much larger amounts of information than previously possible. Recently, Ramna and I have turned to the problem of dealing with large tables.
For example, this is a table of the 1986 baseball statistics with 323 rows of players and 23 columns of data. We can put the data into a spreadsheet, but even using a 21-inch workstation display, the data requires 9 full-screen vertical scrolls and 2 horizontal scrolls, making it hard to work with. It's hard to find players or see interesting patterns. In short, it's hard to make sense of the information. We've devised a new way of visualizing and interacting with large tables called the TableLens, which exploits graphical representations to compress the information onto the display. In this column, at bats, we integrate a familiar bar chart representation directly into the textual view of a table. Some of the rows, those in focus, show underlying textual values along with the graphical bars. Other rows, those in the context, show only graphical representations, thus requiring less space. By displaying the entire table graphically, with only some of it in focus, this 324-row by 24-column table can be shown using a portion of the screen. The TableLens displays 30 to 100 times as much information as a spreadsheet in the same space. With a small set of manipulation operations, the TableLens allows fluid navigation and exploration of the data. The focus area can be manipulated using control points and/or keyboard commands. The number of cells in the focal area can be increased or decreased. The focal area can be moved to different rows or columns. Since the essential geometry of the table is preserved, multiple focal areas can be created. To facilitate browsing of context cell values, a mouse feedback area at the bottom of the window shows column, row, and value information. Here, sorting career at-bats reveals correlations in several nearby columns. Notice that career hits is strongly correlated or proportional to at-bats. In other words, most players have similar batting averages. Some players stick out from the curve, 2 well-known batting stars, Wade Boggs and Don Mattingly. To confirm these observations, we divide career hits by career at-bats, creating a new column, career average. The batting average curve is reasonably flat, as the correlation of the curves suggested, though increasingly noisy with decreasing career at-bats. Furthermore, the length of the bars shows that Boggs and Mattingly have the highest two career averages. If we focus on the salary column, we see that Boggs and Mattingly are paid relatively well for their top-flight batting performances. Also note that salary is somewhat correlated with career at-bats. Team and position of a player categorize players into different groups. Category values are displayed using blips. In focus columns, the blip is colored and positioned in the cell according to underlying value. In context columns, since space may be tight, only color is used to indicate the value. Sorting on position separates the players by category. In other words, all like-colored and positioned blips are brought together. So this red line is all the third basemen. Coding effects can be readily spotted. These isolated blips indicate players that play multiple positions and thus have unusual position codes. Sorting by team, other interesting patterns emerge. First, we can see that each team carries a complete stable of player positions and that the sporadic blips are scattered. Second, notice that most of the teams have the same number of players, though two lines are about twice as long as others. This is another coding effect. These lines are Chicago and New York, both of which actually have two teams. Nearby, two other category columns, division and league, have become more orderly, indicating a relationship to team, or in database speak, a functional dependency. Since the noisy areas align with the Chicago and New York players, perhaps we can exploit these variables to separate the merged team codes. In this next scenario, we perform a common kind of analysis in which quantitative data for different categories is compared. First, we sort position and hits to obtain the distribution of hits for each position. Comparing these batches, the second and third from the bottom stand out somewhat as having more large values. These are the first baseman and right fielders. Reasonable positions in which to play strong hitters with less than stellar fielding skills. Other nearby columns show some dominant groups. Further investigation reveals that these columns are putouts, in which first basemen and catchers dominate, and assists, in which the infielders dominate. An alternative for observing the relative performance of a category utilizes a technique called spotlighting. The blips for players of interest are accentuated using a red line, and then the quantitative column of interest, hits, can be sorted, in this case revealing that the right fielders band toward the top of the distribution. Here, we look at Xerox stock data for 492 trading days. This table has columns for date, volume, high, low, and closing price. The graphical representation for dates is similar to the one for category variables. Each month is given a span in the column, and three colors are used for the first, second, and third months of a quarter. Thus, we can see that the table includes just over a year and a half of data. Blank lines in the data indicate trading holidays. These two nearby lines must be Christmas and New Year's Day. We can explore the relationship between daily trade volume and daily price range. First, we calculate the daily price range from the high and low, and then we sort by volume and break the table into quartiles. We can see that most of the really high range days are in the top quartile of volume. By reordering by date and calculating closing price minus the previous day's closing price, we can examine the daily change in price. And now, sorting on the change, we can view the top change days. By sorting volume, we see where these big change days fall on the volume distribution. Most appear on big volume days. The well-known buy signal sought by technical traders is a large jump on large volume days, in fact, like the days currently selected. By sorting on date, we can examine whether Xerox stock rose in the period following these technical indicators. Here, we see that the recent Xerox price climb started from a pair of these big jump, big volume days, and 4 others occurred during this rally. Here, We have 406 cars sorted by gas mileage. The Japanese cars, indicated by red lines, dominate the high MPG cars. An unexpected advantage of TableLens is that sorting is useful for navigation as well as analysis. Let's say that we want to find the Toyota Cressida and we know that it's a Japanese 6-cylinder car. So we sort by cylinders and then by origin. We can then focus on the Japanese 6-cylinder cars to find the Cressida. Though textual search may be faster, this technique will work without a keyboard, for example, with a pen device. Furthermore, sorting organizes the nearby space. Here, other Japanese 6-cylinder cars are now nearby. Thus, this direct manipulation technique provides capabilities similar to a hard-to-use relational database query.
The looming advantage of the TableLens is the space advantage. You can visualize and manipulate this much information and more on a single integrated display.
The TableLens also makes it easy to navigate around a table without getting lost, to perceive patterns or find interesting cells, and to explore relationships between cases and variables. In short, it allows running your fingers directly through the information, making sense of it.
Okay, so that was TableLens. I want to apologize. There's a couple of screw-ups in the video. I'm scrolling around a little there. But in essence, what's going on is that selection is being used quite a bit in order to be the starting point of a further suite of analytical techniques, in particular sorting and selection. Here we're showing an example of using TableLens, the commercial version of it, to select and show me more details on demand. And that's shown here. Global funds, a particular mutual fund has been selected in this visualization of a database of mutual funds. Clearly, selection is an element, is the primary ingredient that you need to be able to do to exercise your the kind of next steps in interactive analysis. The other thing that it was probably obvious, as you saw, they were exploring the use of gesture. In that case, by drawing an ink trail in order for that to be a means of interacting with the visualization. That was something that was being explored at that time. Also, if you wondered who Stu Card was, he's one of the founding parents, if you will, of interactive computing. He started at Xerox PARC in the early 1970s, and his work has been foundational to the field. One of the things that you often see used in tools like TableLens is pop-up tooltips, where you hover the mouse cursor to bring up details of an item. You also see that as the first step when you're selecting to do details on demand. And so that, for example, in the previous slide, the one about selection, that details on demand thing is a term used in InfoViz when providing the viewer with more information and details about a data case or cases. And it may just be more info about a case, or maybe moving from an aggregate view to an individual view. If you're selecting a bunch of things, the aggregation information is going in the opposite way. You want to do and create an aggregate of a bunch of things, possibly, particularly if you say that's what you want. And so selection is used as a starting point of some kind of dialogue or some kind of syntax whose job it is to activate the things that you wish to activate. It may be moving from aggregate to individual, may not be showing all the data. The reason why that might happen is the visualization might not be showing all the data due to a scale problem. There's just too much stuff, a bunch of things being overdraw. You also may be showing some abstract of a group of elements that you'd like to break apart and see the details of, and expanding the set of data to show more details. The examples we've shown here in TableLens, you do actually see that going on, where when you click on something, you see the full size line. When you deselect it, you see the line shrunk down to a single pixel, and that's kind of one of the key insights of TableLens, is the ability to do that. Another thing that can be very important for in the use of selection is to use that to select not individual items here showing, the row, but also to select elements for the purposes of rearranging the view somehow. In TableLens, it's particularly salient of, say, dragging, say, the quarter to be close to something else here, quarter and year, to drag those next to, say, the index or some other value that you want to juxtapose visually. And that's something that you do see. You also saw sort quite a lot in the TableLens video. Finally, one of the things that you see selection used for a lot is as a means of inputting to data. This is particularly true of more modern tools. It's something that I've kind of talked about a little bit over the last couple of weeks about the use of selection and making marks and so on and so forth on the data for the purposes of you recording as an analyst your understanding of the data and perhaps positing a relationship or confirming or denying a hypothesis or something like that. And so the little examples that are shown here are showing examples of free-form pointing and capturing as a means of documenting what you're thinking about with respect to the data. So over here on the upper left, we see that that two peaks have been circled or ellipsed, if you will, the red thing indicating a strong peak and the blue circle indicating a short peak. Here, there's been a selection made in order to do some kind of further annotation about what's going on in that particular, that's in the Los Angeles area. Over here, drawing the curve, sort of in an ink trail for the purposes of communicating perhaps to a colleague that something interesting is going on with that data. And over on the right is something I think we'll talk about in the further a little later on in the lectures, taking a range of values of data in order to engage in focusing on them. So that's basically it for the lecture 8.2. I should have put 8.2 in the label there. And that has been about selection and tooltips.